addressed by Schrödinger problem since the 80s. Since then, with a periodic ideological contest, in the sense that, in his view, the result of Schrödinger problem is a kind of statistical, classical statistical regularization of a classical theory. So the parameter of this regularization will be something like a Boltzmann constant. And for my side, it is a quantum-like regularization, and my constant is the Planck constant. So in spite of this, we are still in very good terms. And the proof of this is that he's going to reinterpret now Feynman-Kac formula in terms of its favorite regularization, which is the entropic one.
All right. So, hello everybody, and thank you to the organizers to provide us with a real meeting with people in a room. Yes, so it's a real pleasure. What I'm going to talk about a very well-known formula, which is the Feynman-Kac formula. At the very beginning of, let's say the first part of my talk will be about this Feynman-Kac formula. So it will be, there will be a lot of probability theory inside. But for those of you who are not acquainted fully to stochastic processes, I will wake you up at the end of my talk, because I will talk about a little history of the Schrödinger problem and the Schrödinger equation, and you will see. Okay, so it will be talking with the ends and maybe describing a program for the future. So Feynman-Kac formula under a finite entropy condition. So the Feynman-Kac formula is the following one. This is this blue formula. So you look at this linear parabolic equation. So I have to be careful with the mouse. Maybe, no, this will be, okay. So you, it's hypersensitive, bad. So it will happen very often, probably. Oh, all right, so you have this gray parabolic equation, and this is a linear equation, and the boundary condition is at the final time. So I will call during this talk Feynman-Kac equation, but this is simply a linear parabolic equation, okay? And the very well-known result about Kacs is that when everything is regular, you can have this blue probabilistic representation of the solution of the gray equation, of the FK equation. So the people in this blue displayed formula is X is the canonical process. That this means that X is the position at time t of a Markov process whose law is R, the Markov measure that you can see here. Okay, V is the potential, and GT is the final boundary condition of the parabolic equation. And what is performed here is a conditional expectation, knowing that the position at time t is X, and you look at the future, you go to small t to capital T, this is in the future. And the Markov measure is associated to the linear, this part of the equation, which gives you the Markov evolution. So for probabilists, this means that R is the solution of the martingale problem, MP, with the diffusion matrix A and drift field B. And under smooth hypothesis, this is a well-known formula. the rule of the game is today that A is allowed to be regular, as you can see, invertible. So this means that, well, no hyper-coercivity condition and so on. But especially the potential V and the final condition GT are not assumed to be very regular and to have strong growth restriction. So for the motivation, I would like to study the Schrödinger problem with a potential V, which could be in a Kato class. So no regularity. And the function G, as you will see, is one of the two functions solving the Schrödinger problem. This is this one here. Oh, sorry, I have to be very careful not to switch. So you see the Schrödinger problem is the first blue formula. The aim is to minimize the relative entropy, which is of H of P with respect to R V, and RV is the Markov measure R multiplied. This means that you have a Radon-Nikodym derivative, which is the exponential of this action, which is the time integral of the potential along the trajectory X. And P is a probability measure. R is simply a non-negative measure, sigma finite, but P must be a probability measure with prescribed marginal, at time 0 and time t, so mu0 and mu t are prescribed. Well, under very large hypothesis, we know that there exists a couple of functions f and g, f0 and gt, such that the unique solution of this convex problem can be written in this form. So R is the Markov process associated to the diffusion matrix A and the drift field V, and you can have this solution. And F0 and GT must solve the Schrödinger system, which we already saw in Toshiomi-Kami's talk, and which is this one, okay, where as a notation, so F0 is given, but Ft, F capital T, is given by Feynman-Kac formula. And so, for instance, GT is given and G0 is given by this formula. Okay? So, how to prove that we get this Schrödinger system? So, you know P, take this form of P for granted, and then if you want to compute the first marginal at time 0, well, a general probability formula tells you that with respect to R0, the Radon-Nikodym derivative must be the conditional expectation of dP over dr knowing x0. So this is general stuff and easy stuff. So you plug in the expression in blue, F0 comes out because it depends on x0, and you're left simply with this term, which has a definition, is called G0. Okay, this is so the natural thing you have to look at when looking at the Schrödinger system is a Feynman-Kac formula. All right, this is given for free. So now the question is this Feynman-Kac formula, which is given for free and which can exist under very mild hypothesis, because everyone here is non-negative inside the expectation, so that even if this expectation takes the value plus infinity, it makes sense to have the expectation of a non-negative quantity. So we know that if everyone is smooth, there is some parabolic equation which is associated to this formula. And now I would like to do the real thing is if V and G are not smooth, is there any parabolic equation associated to this? So we know that viscosity solutions under mild condition are the good candidate, but these conditions, for instance, are all right if G and V are continuous in some sense. You need some continuity somewhere. But in the Kato class, you are essentially bounded, but it can blow up at one point. Think of Newton potential. And this is a very natural potential to look at. So this is the motivation. It will be a little technical, as you can guess, but I will try to make it as easy as possible. So the hypothesis that I work with is simply that the entropy of P with respect to R is finite, where P is this solution. Okay, so the data now are F0, GT, V, and R, and the hypothesis is this term, this finite entropy. And as a first theorem, well, we define G as being the Feynman-Kac formula, which is always defined because of positivity. So suppose now that GT is positive, non-negative. Then it's possible to show that this function of T and X belongs to the domain of some operator. And this operator, I call it LRP. And this LRP is a Nelson derivative. And in fact, this is what Meyer, Paul-André Meyer, called a stochastic generator. Okay? And this solution can be solved this type of equation where you have this capital L plus V applied to G is equal to 0. So if G is smooth, L of G is simply this operator plus V. So you're back with the parabolic Feynman-Kac parabolic equation at the beginning. All right. So this is a natural generalization of the usual classical sense. Here, there is something important. This is only true P almost everywhere. And P is the solution. Okay, this is not true R almost everywhere, but only P almost everywhere. And this is the key thing to note, because nothing explodes P almost surely, but it could explode if you go far away and, for instance, everywhere, or even R P almost everywhere. Okay, and this is an almost everywhere notion. So what we get is a pathwise notion of a solution to some extension of a parabolic equation. So as definitions, I go very quickly. This is for probabilist. What this operator is and its domain is, we say that a function u of t and x belongs to this domain if u of t and xt is a semi-martingale. So q is your reference measure here. And this means that you have some bounded variation process plus some q local martingale, local q martingale. Okay? And there is a key assumption here. There is a dt. Any bounded variation process is not absolutely continuous. So this dt means that the bounded variation part of your semi-martingale must be absolutely continuous. And this is sometimes a nightmare to prove. So, so it's included in the results, okay? And when I recall what local Q martingale is, this is essentially a martingale, but it's more general in the sense that you can have a sequence of increasing stopping times, tau k, tending to infinity or more surely, such that the stopped martingale at each tau k is uniformly integrable Q martingale. So it's a large class of martingale in some sense. And I skip the technicalities about P here, which is inside this hypothesis. So as I told you a couple of minutes before, the result is true P almost everywhere. So we need to have a sequence of stopping times, tau k, which tends to infinity, not Q almost everywhere, but only P almost everywhere. This is the only difference. So this makes things work, not rather easily, but it works. I hope so. So now there is a similar results about Hamilton-Jacobi equation. And what is Hamilton-Jacobi equation? When you start from this Feynman-Kac equation here. So write this Feynman-Kac equation in this form where A is simply the Markov generator without the time derivative. So you can write dt plus A instead of L, okay? And this is here, you have the FK equation. If A satisfies a maximum principle, which is the case where when A, the matrix A is a symmetric positive matrix, then and GT, the final boundary condition, is non-negative, then non-negativity is conserved all along the time, the reverse time, and you can write G equals exponential some function C.
Even for very nasty potentials? I
Uh,
thought this kind of weak comparison principles were very delicate to potentially singular. Somehow. No?
well, maybe. Well, I don't use it in some sense. No? I don't use it, but the Kato class is all right because they are essentially bounded. Okay. So I would say the singular points are at a zero measure. Okay. So you keep this non-negativity here, and you can simply write G equal exponential Psi, or Psi is the logarithm of G. But this slide is completely formal. Okay, so this is just to have an insight of what I plan to do. Now take this parabolic equation, apply to G, which is written as an exponential, and multiply it by the inverse of G here. With simple computation, you arrive at this equation. Okay, V is here, and you have a nonlinear operator here. And this nonlinear operator is in fact the linear operator A plus a nonlinear contribution, which is simply, it would be zero if A was a derivation operator. Without the Laplacian, it would be zero. So this is what comes in when you put some diffusive motion in the framework. And if you do easy computation, then you're back with the usual carré du champ, half the carré du champ. And again, the carré du champ is measures some deviation from, if A was a derivation, then A of psi square would be 2 psi hc, and you measure this deviation. Okay, this is simply a remark, but I like it. I don't know if there is anything deep in it, but that's it. Okay, so this is in a smooth setting, you get this Hamilton-Jacobi equation, which is here. So you see the usual linear term plus the carré du champ plus V, and a final condition here. And if everything is smooth, then I rewrite here in terms of stochastic differential equation, what means R to be a solution to the Martingale problem associated with matrix A and drift B. This means that the xt is B dt plus square root of A and a Brownian motion with respect to R. So you have R here, and here you have P. P, remember, is the Schrödinger bridge, which is the solution of the Schrödinger problem, which is written in terms of F0 exponential V and GT, okay? And with usual computation, which is the computation of H process, then you can show that P is in fact solution of the martingale problem, where the drift is not B anymore, of course, but you must add A times the gradient of psi, which is the solution of the Hamilton-Jacobi-Bellman equation. So there is, this is very straightforward computation. And this is very well known. And this was part of Professor Mikami's talk this morning, okay? So recall these two formulas, and the theorem regarding the Hamilton-Jacobi-Bellman stuff is that, again, under the hypothesis that the relative entropy of P with respect to R is finite, if you define psi as being log of this conditional expectation, then you can show that psi belongs to the domain of the stochastic generator, extended generator in the sense of Paul-André Meyer and the Strasbourg school. And psi satisfies this new notion, extended notion of Hamilton-Jacobi-Bellman equation, where you see the linear part plus the carré du champ plus V is equal to 0 P almost everywhere. And P solves a martingale problem where instead of this gradient, if C is regular, this is the usual gradient, but you have a new kind of gradient. And what is this new kind of gradient? It comes from an extended Ito formula, which makes sense under this finite entropy condition. So, well, you can believe me, there is, but what I should say, I use the invertibility of the matrix A at this point because it is needed to have a martingale representation theorem. A martingale representation theorem tells you that any square integrable martingale with respect to a Brownian filtration is in fact stochastic integral with respect to this Brownian, and this gradient tilde is the integrand of the stochastic integral in this formula. You can see it. So if everybody is smooth, let's say U is C1, 2 in time and space, and you can play with the usual Ito formula, which is written here, then, and if X as a drift V, dx can be written in this form. You plug it into the formula, and what you get is this. This is very usual, but now the difficulty is to show that if U only belongs to the domain of the extended generator, you have some notion here. And this is given by a martingale representation theorem. All right, so the guideline of the proof for the Hamilton-Jacobi-Bellman equation is as follows. So as a definition, you write these HK formulas as conditional expectation, all right? Formally, what you get is that G, again, is solve this parabolic equation in G, and F solves the time-reversed parabolic equation. There are two differences, minus sign here, and not the same, the usual boundary condition with the initial time, okay? And so this is forward in time, backward in time. And you will see that these two equations are fundamental in the 86 paper by Jean-Claude Zambrini. Huh? This is, they will play something, a role in Portugal.
Only one to this?
Oh yes, you're right. There is something missing here. Okay. No, only one drift. Only one drift. Only one drift. So because this is with respect to. Now, what we are going to show is, oh, sorry, good. I should have another drift here. There is some, sorry, thank you, Jean-Claude, for this thing. So if here you have B, here you should have a B tilde, something which is different and in connection with the time reversal formula. Sorry, we'll go back in there. Okay, so now let's show the Born-like formula, so which was at the very beginning of the idea of Schrödinger to address his problem, the Schrödinger problem, to mimic quantum mechanics, usual quantum mechanics. So you start from the definition of P in terms of F0 exponential V GT, okay? And you write this Radon-Nikodym derivative. Very general formula. You just take the conditional expectation of the whole Radon-Nikodym derivative, you plug it here into this conditional expectation with respect to R, and you split at time t. And so you split the exponential, and what you see is that on the left side, it only depends on the past at time t, and on the right side, on the future at time t. Since R is assumed to be a Markov path measure, then the exponential of the expectation of the product is the product of the exponential, is the product of the expectations, okay? So what usually our students write without bothering, but in this case, this is true, all right? And so you're back with FTGT, and this is a one-line proof of this Born-like formula, okay? You do the same, but if you, instead of time t, you look at all the future at time t, and if you apply Ito formula at some place, what you arrive at is this formula. You have at time t, the law at time t, and where are you? Okay. And then applying Ito formula, suppose that C is as regular as you wish to apply Ito formula, then you get this. So I skip the details, but as you can see, the computation is quite straightforward. There is no difficulty. Well, what I do, again, I split at time t. Since I only condition on the past, then the past gets out of the expectation. Ft is the definition of the left and right end term, the left end term. And so you get, now you force GT to get into the picture. And this is, you divide by GT with this term, all right? And FTGT, we've already seen that this is the initial distribution, and you're left with applying Ito formula here with this term. All right? So this is this formula. I write it again. And now we compare it with Girsanov formula, which can be written in this way: initial distribution at time t, and in the past, you have some stochastic integral with respect to the natural martingale for the R process, and this compensator here, which is in terms of the half square as usual for people doing stochastic processing. So this means that P solved the martingale problem with the drift A times beta, where this beta is here. And now you identify. Of course, it's not so easy to identify, but formally you can do it. And what you see is that beta is the gradient of C, the solution of the Hamilton-Jacobi-Bellman equation. And then if you identify this bounded variation term with this one, then you're left with the Hamilton-Jacobi equation for C. Okay. So that's it. And this is the guideline of the proof. And of course, it's not so easy to put it on a solid ground with because I used Ito formula, and we have to be careful. But this is the main idea. Play with semi-martingale, avoid Ito formula, but use martingale representation theorem instead.
But when if you can do this and you identify those terms, so this means that the solution is some strong sense.
Yes, the solution is in this sense. This means, as a definition, define G as being this Feynman-Kac formula. You don't know if it's regular as a function of X. So X is here just behind Luca. And as a function of T and X, you don't have any a priori smoothness from this. But you can take the logarithm because this is non-negative. You can include the value minus infinity, log of 0. Okay.
So and the fact that P is Markov is here for free because you define P to be exactly.
Oh yes.
Usually you have to first prove.
Yes, P.
And then
Yes, good remark. Yes, yes, of course. Yes, we can show that P is Markov because it's defined as being F0 exponential
V.
V.
That these singularity can destroy the Markov property, right?
No. It's really it's algebraic. You see. All right. So
But again, you have this equation where over X, P almost everywhere.
this is only P almost everywhere.
Now, you have a density of X with respect to some reference measure.
X is the process. Oh, you mean the law of the process? Yes, it is absolutely continuous with respect to R because there is a finite entropy. This is the hypothesis.
So if you write it on the space, the equation, I'm trying to figure out what does it mean, the equation on the space, not on the process.
Oh, on the space, this is this one. If everybody, the green one, if everybody is regular.
Yeah, right, but it falls almost everywhere.
Almost everywhere, yes, you see. So, but there is something more. Then you can follow it pathwise, yeah. But it's only almost everywhere and P almost everywhere. So you avoid the place where you could explode and so on. All right, and I think this is the.
So you're kind of guaranteeing that your canonical process does not enter the bad region, right?
So, no, it guarantees that it never goes to the bad region in the view of P. Yeah, okay, yeah. But in the view of R, which is where you have you can explore larger areas of space. Then okay, it's only and because all right, because there is this P almost everywhere. You can write everything you want in some sense. So the main difficulty here is that if V is non-regular, for instance, is you choose V to be in some Kato class, then Psi equals log G is a priori non-regular, and you don't have Ito formula. Okay, so you have to work with stochastic derivatives, the curly L's, and I've only shown the guideline for Hamilton-Jacobi-Bellman equation, but once you've got the Hamilton-Jacobi-Bellman equation, it's very easy to get the Feynman-Kac result. The first theorem that I wrote, just going writing G is equal to exponential to psi, exponential of psi. Okay, so what is really important is Hamilton-Jacobi, because and Hamilton-Jacobi appears inside the Girsanov formula. And this is the idea, and this is probabilistic. Okay. So, what about this hypothesis? P should have a finite entropy with respect to a given R, which is the main hypothesis. If you write it, then what you get is something which is, I would say, a reasonable requirement, because you want, for instance, that this action along the potential V should have a finite expectation, which is at least what it's very difficult to go below such a condition. But it's not explicit because it depends on the solution that you want to have some information on. Okay, so if you write the explicit form where you have the log here, but you have to put the Radon-Nikodym of P with respect to R, and R is explicit, then you have an ugly condition. So you have to do some work to find out some easy to use a criterion, for instance, when V is in the Kato class. So this is quite technical, but I only give a simple example where R is the Brownian motion, the reversible Brownian motion starting from Lebesgue measure with some epsilon in front of it. And you should only ask that F0, well, F log L and F log F and G log G should belong to some LP spaces, and that the positive part of the potential should be in the Kato class, and nothing is very required. The negative part should be L1 log. So this is the type of result we can get, and which makes sure that you have a finite entropy condition. Okay. So how much time again? So this is the second part. You can wake up. This will be 15 minutes. All right. So this is a brief history of the subject, and in green, the code is Schrödinger equation. In blue, Schrödinger problem. Okay. So Schrödinger equation is here, 1925, and Erwin Schrödinger was very much inspired by an incredible idea by De Broglie in 1923, which is the duality, the wave-particle duality. Okay, so quantum object behave like particles sometimes, like waves some other times, and Schrödinger wanted to work out his equation. And what he did, and I talk under the control of Jean-Claude, but it seems that what he did is in 1925 paper, which is Nobel Prize paper, is that it started from Hamilton-Jacobi equation, because Hamilton-Jacobi equation is very natural in mechanics. So this is for doing particles, but also it has some wave propagation inside of it, and which looks like a wave property. So this is a key equation to go to this linear equation. And what Schrödinger does is that then when he works with the Hamilton-Jacobi equation, not Bellman, Hamilton-Jacobi, then it takes the logarithmic transform and goes back to his linear equation. So this is at the very beginning. So sometimes we say that Fleming did it in stochastic control. Yes, he did it by himself, surely. But Jean-Claude told me a long time ago, but well, they should say that this is the Schrödinger transform. And it seems that this is the first occurrence of this logarithmic transform, okay? And then 1 year later, in 1926, you will see Madelung did some computation, and which will be very important for the future, even for the future from today of quantum mechanics. I hope so, as you will see. In 1931-32, this is blue, so this is the Schrödinger problem. You all know about it now. And then you have to wait a long time. David Bohm in 1952, it seems that he didn't know about Madelung paper. And he did the same computation as Madelung, and where some Hamilton-Jacobi equation, I will show them in a moment, appeared. And it took this computation very seriously as a physicist. And he goes one step forward from Madelung, and it creates what will be called Bohmian mechanics, which is, as you will see, very close to the Schrödinger problem. And Jean-Claude in 1986 was a postdoc student of Nelson, and Nelson developed during the 60s, from 60 and 70s and the beginning of the 80s, is stochastic mechanics. And Jean-Claude discovered by himself the Schrödinger problem in the literature. And he went back in, and he was, I think at this period, you met Jamison also.
Yes.
Yes. And so you.
Nobody had read this paper.
Yes. So, and Jean-Claude is in a situation where he's supposed to do stochastic mechanics with Nelson. So there is some Brownian motion, and he discovers the Schrödinger problem. So he mixes them together, and it gives birth to Euclidean quantum mechanics, which is, in some sense, all the Schrödinger problem stuff. Okay. Then we have to wait a little time, and Max von Rennesser here in this room. I knew that Max was a fan of Brownian mechanics, and he took it seriously. And at this period, as you see, optimal transfer was very much understood. And as you will see, what Max did in his 2009 paper is that he shows informally, I mean, as a physicist, that Schrödinger equation is in fact a pure Newton equation in the Wasserstein space with Brownian potential in the picture, okay? And in 2017, Giovanni did the same thing, but for the Schrödinger problem. So this means that in the main impetus comes from Max's paper, but this is formal. This is a formal manipulation, and a lot of mathematics should be done right now, and it's open to everyone. And Giovanni, look at the Euclidean version of stochastic quantum mechanics, went to the Schrödinger problem, and could do proper mathematical computations under some restrictive assumptions. So I will present this, and all these contributions deal with a notion of Newton's equation. Okay, so let's go and see this. So excuse me, Jean-Claude, but I have to write the wave function of the Schrödinger equation is the letter chi, which is here, because psi is already used. This is psi is equal log g. So so it won't last very long. Be patient. So this is the usual Schrödinger equation. So if you want to see it written with the usual psi, go back to Toshio Mikami's talk, where this is exactly the same equation in the forward time. So, but a Schrödinger equation is a complex valued equation. So it means as it is two real valued equations, the real part and the imaginary part. Okay, so it contains two equations. So if you want to simplify it a little bit, divide by h bar, and you are here. And then if you want to see a completely equivalent equation, take the complex conjugate. So you make it here, and there is only difference. So you put bars everywhere, but here there is a minus. And this minus means that this is minus t instead of t. Okay, so you reverse time. And all right, so in fact, you can look at the Schrödinger equation as in both sense of time and look, and it contains exactly the same evolution. So what Jean-Claude did, he took these two Schrödinger equations, did this, instead of it, decided to write t, instead of v, decided to write minus v, and then formally what you obtain from these two Schrödinger equations, you obtain these two parabolic equations in the two different two sense of time. This time b is equal to 0, so there is no problem. The drift are there are no drift. Okay. And so this is the idea of Schrödinger in his 1931 paper. But Schrödinger didn't write v is equal to 0 in his paper, and Jean-Claude did the mathematics with v where everything is supposed to be smooth as you wish to, because this is a physicist. It's even more. It's published in a physicist review, physical review, I think. Yeah. Yes, and all right. The idea of Schrödinger about this Schrödinger problem is the following one. The Born formula is that the density of finding a particle somewhere at time t is simply the square modulus of the wave function, and with respect to Lebesgue measure, and you can write it as the product of chi and chi bar. Okay, and Eddington, the famous Eddington, who did the experiment, the astronomic experience, which was the first empirical proof of that general relativity works. Okay, this was during an eclipse. Okay, during the First World War, and this is the same Eddington. And Eddington says, okay. In the Portuguese colonies, this is important. Okay, this is a quote by Jean-Claude. Okay, and what Eddington remarks is that you can propagate the Schrödinger equation forward and backward, and then when they meet at t, you just do this product, and you get the density of the particle. So Schrödinger take it seriously, but in a thermodynamic setting, and this is the FG setting that he thought of. I don't know how is it possible to think of it. This is pure genius, to my opinion, but he did it, and we know the Schrödinger problem for this. All right. So the question now is, instead of a Cauchy problem, you have a boundary value problem. But this boundary value problem is well posed for the thermal evolution, I mean for the Schrödinger problem, because it's very natural to have a boundary value problem, because you don't have any notion in a diffusion motion. There is any natural motion for a momentum, an initial speed. Okay. In fact, now there is Nelson derivative and so on. We can work this way. But, well, boundary value problem, you only know the position. You only need the position and not the momentum. And for a quantum evolution, it's oddly designed because the momentum is built in the wave function. So it's not so natural to have a boundary condition. What is natural is a Cauchy problem. Okay. Anyway, so the question is, okay, you have a boundary problem, how to select the velocity. So for the thermal evolution, Schrödinger, when he designed the Schrödinger problem, used the maximal entropy, the Gibbs-Boltzmann maximum entropy principle, and this produces this design, the natural velocity field, okay, which is B plus A gradient psi, okay? And this was really written properly for the first time by partly Jameson, but essentially in the Jean-Claude paper in the 86 paper. Now, if you want to have any notion for the quantum evolution, if you keep stuck to the orthodox interpretation, so you stupid exam failed. No, you have only position. If you look at the position, you can say anything about the velocity field. Okay, well, so but not so stupid. There is a possibility to walk around, and this is the de Broglie-Bohm way of looking at quantum mechanics, and this is in this setting that Max wrote his paper, his 2009 paper about the Newton equation in the Wasserstein space. So let's see below. I'm running out of time, but well, a few minutes. Thank you. So what I'd like to stress is the importance of Hamilton-Jacobi equation. We already saw Hamilton-Jacobi-Bellman equation inside the Girsanov formula can give us something. But now, if we forget the Bellman part of the Hamilton-Jacobi equation, what we have, if you look at fluids, then a fluid evolution, then you have this dynamical system. So an ODE, which with a drift field, which is V for velocity, and you push forward an initial density, mu0, and it gives you mu t. So there is a notion of total derivative, which is capital DT, which is here, and it serves to write this. This is an integral, so you can write this. This is simple computation, and also you have the continuity equation. Okay, so the velocity appears as the total derivative of the identity. Okay, and you have a notion of acceleration, which is the total derivative of the velocity, which is this. Okay, so far so good. And we, in fact, know if we work in optimal transport, we know this phenomenon. So I write here the connection, natural connection in the Wasserstein space here. And this is essentially this total derivative, but you have to project it on a gradient, a space of gradient in L2 of something. This shall not be needed here. And for instance, with quadratic transport, which is a very important transport connected to Brownian motion, by the way, then the velocity field is the gradient of some function theta. And the natural velocity of the McCann interpolation is mu dot as a definition, is simply this gradient. This is the insight of Otto and of Felix Otto. So you have this. Well, X is identity, sorry. Yeah? And so if you want to work out the acceleration, you just do simple computation. I write the total derivative here, and then what appears is something which is typically in the Hamilton-Jacobi equation. And in fact, this is, so Jean-Claude a long time ago told me, you don't know the gradient of Hamilton-Jacobi, it's well known, it's Newton equation. So, wow, so I didn't remark it, but it's true, and this is the proof. So you write this Hamilton-Jacobi equation. So it's not Bellman because you don't see the Laplacian, you just take the gradient, and we have seen that the gradient of the first part here is simply the acceleration in the Wasserstein space, and the acceleration in the Wasserstein space is simply the usual gradient of V as a gradient field, but it appears to be the minus the gradient with respect to the Wasserstein structure of the curly V, which is defined this way. Okay, so this is in a nutshell the importance of Hamilton-Jacobi equation. So Madelung, I go very quickly, did this polar decomposition. So key is the wave function. You write it with its real part and its imaginary part. And if you write, you plug in this expression of key in Schrödinger's equation, then you have two real valued equations, of course, one for the real part, the other one for the imaginary part, and you're left with a continuity equation here. Well, oops, sorry. You're left with a continuity equation here and an Hamilton-Jacobi equation. This was Madelung computation, and with a bizarre word term, which I call curly C of mu, because curly, which is simply Laplacian of R divided by R, is as a dimension of a curvature. This is the reason for C. Okay, so Bohm took this computation very seriously, and he says, okay, quantum particle follows the solution of some Newton equation with the usual potential V plus a quantum potential, which depends on the whole solution, but only the distribution of the the presence of particles. Okay, so what Max did is, and this is a capital insight to my opinion, is that he discovered that in fact, if we go at the level of the Wasserstein space, then what we obtain is that this quantum potential is simply some Fisher information of mu, and which is quite amazing, because the Fisher information has a physical meaning. It is simply the entropy production. When you are at mu, you take the heat semigroup with this time here at t equals 0 with respect to the equilibrium, which is the Lebesgue measure, and this is this quantity. So there is something to do with the Brownian motion, but in a bizarre way, as you will see. So the result, which is a formal result by Max, is that the Schrödinger equation is Newton equation in the Wasserstein space with the potential, which is the usual potential, plus some Fisher information here. This is my last slide now. So what Jean-Claude did, again, as a postdoc of Nelson in '86, he did the Madelung transform in the Euclidean quantum mechanics settings. So F and G, this is the F and G of the Schrödinger problem, our real valued problem, our real valued function. And you can always write this. So beside this, this is R square. U is equal to R square as before. It was written, but still hidden. Okay. And what we obtain here is exactly the same equation, but there is a plus instead of minus. You see? So the quantum potential appears here, but with a plus sign, a reverse sign. Sorry. Hi, Erwin, it's you. And what Giovanni did is that the solution of the Schrödinger problem, if you only look at the time marginal, we call it the Schrödinger interpolation, solves Newton equation in the Wasserstein space with potential, the same as Max, but with a minus here. And it changes everything. This minus makes things easy. This is the usual way where you have the thermal equation, thermal world, and so on. And this is an entropy production. Okay, you have the usual heat flow. What does it mean? That in the quantum world, you reverse, you have something like an anti-Brownian motion or something. And this is not true that this is reverse time, because reverse time gives you exactly the same acceleration. So this is completely different. Completely different. So this is why you can, with thermal motion, you have relaxation, slow relaxation to equilibrium. And if you reverse the Fisher information, what happens? So I have my end, sorry. So you have minus Fisher information is something like this. So to relax, you put something and it goes in infinite time to a non-stable equilibrium. Now, if you, in the quantum world, we have something like this, and you have oscillations. But, well, there is some physical meaning of this, but I'm getting crazy to find some meaning, and thank you for your attention. So just maybe, this is important for me, because usually Erwin Schrödinger is known for his equation, for his main discovery about quantum physics, but he was completely fan of Boltzmann. And this is the cover of a series of lecture notes that he gave in 1944 in Dublin. And so, well, I like it. This is the main connection. Thank you.
As usual, if anyone online has questions, how should I? No. I should try to find. No, that's fine. Yeah, screen sharing is finished. Oh, chat. No. Okay. So maybe someone in the audience. Of course, yeah.
Maybe just an historical comment, because the last 15 minutes was digging into history. For those who are interested by Madlung, the huge paper written, published a few days ago in the Bulletin of the AMS by Boris Kesin and two other scientists is all about Madlung in any possible degree of generality. So it means that this is...
Which paper?
This is a paper of Boris Kesin, the student of Arnold, geometric hydrodynamics. And this is very interesting because he relates a lot about Madlung transformation. So maybe geometrically it is maybe interesting too.
Two questions. And the first one is on your finite entropy condition, right? So I'm not sure if I understand correctly. The finite entropy condition is equivalent to that the diffusion matrix remains the same, right?
What do you mean remains the same? It's constant?
No, it's not constant. It's the diffusion matrix under the probability P is the same with probability R.
Yes. Since with this finite entropy condition, P is absolutely continuous with respect to R. And of course, this implies that in this setting, P solves the Martingale problem with the same matrix A as the reference measure. So yes, you're right. This is a constraint, and but a way to see it is that the R is for reference measure. Okay, and as a reference, we choose the thermal bath in which we do this Euclidean quantum mechanics. So this is okay.
Yeah. Okay, so that's why when I formulate the stochastic Lagrangian mechanics, I add a constraint in the path space to let the diffusions have the same diffusion tensor. So, and a second question, in your last several pages, for the Nielsen's mechanics, right? Nielsen also have a extra term related to the curvature, right?
Yes. So yes, you're right.
Oh.
So
thank you.
thank you. It remains for me. This is a good suggestion. It remains for me to compute this extra term and to see if it's coherent with the Wasserstein geometry. I didn't check out this. Okay.
Thank you. Question?
So I think maybe it's time that we stop for a quick break, and we will come back. What time is it now? I think in 15 minutes now. So that will be a short break. Thank you. Oh yeah. Okay.